In our previous lecture, we established the link between the stability properties of the LTI system, x that equals AX, and the eigenvalue locations of the A matrix. Okay, so let's remember our conclusions. We found out that if all the eigenvalues of A are with strictly negative real parts, okay, in other words, if all the eigenvalues of A are on the open left half plane, then this system, x that equals AX, is asymptotically stable, which is equivalent to exponential stability for the LTI system. Okay, if the A matrix has at least one eigenvalue with positive real part, then the conclusion was that the system is unstable. Okay, if neither of those conditions are satisfied, it means that we have an eigenvalue, at least one eigenvalue, on the imaginary axis, and what we do is we check for each of those eigenvalues on the imaginary axis the sizes of the corresponding Jordan blocks. And if we have no Jordan block of size 2 by 2 or larger, we conclude that the system is stable but not asymptotically stable, because well, the very first condition that we mentioned is not satisfied. Or if we have an eigenvalue on the imaginary axis whose Jordan block is of size 2 by 2 or larger, then we conclude that the system is unstable. We reached our conclusions based on previous analysis that we performed on the behavior of the state transition matrix e to the AT and the relation between that behavior and the eigenvalues of the A matrix. And that analysis we were able to perform using the Jordan form of A. Okay, now in this hour we will also talk about other measures of determining stability without looking at the eigenvalues of the A matrix. But before that, since the eigenvalues of the A matrix provide a complete characterization of the stability properties of the system, it's natural to ask whether those conclusions can be extended to the time varying case. Okay, in other words, let's ask the following question. What do the eigenvalues of some time varying matrix A of t say about the stability properties of the homogeneous system LTV x that equals AT times x. Okay, now the answer turns out is the following. In general, nothing. Okay, so we cannot use the eigenvalues in general of a time varying matrix to say anything about the stability of this system x that equals AT of x. So nothing in general. And here is a very nice counterexample from the textbook of Khalil. Consider the following matrix 2 by 2, and suppose that it's the system matrix of some LTV system. The entries are given as -1 plus 3 over 2 cosine squared t, 1 minus 3 over 2 sine t cosine t minus 1 minus 3 over 2 sine t cosine t and minus 1 plus 3 over 2 sine squared t. Okay, so this is our A of t matrix. Now, first of all, it's quite a well-behaving matrix from the entries point of view, because all the entries are sines and cosines, and we have some constant terms. So that means for all times, this matrix will be a bounded matrix. Okay. Furthermore, well, it's clearly time varying because the entries are time varying. But if you compute the eigenvalues of this matrix, there will be some very nice cancellations, and it turns out that the eigenvalues of this matrix are constant. Okay. For each t, the eigenvalues of the matrix A of t are lambda 1, 2 minus 1 over 4 plus minus j square root of 7 over 4. Okay, so it's a complex conjugate pair, but it's time invariant, it's constant, it's fixed. And it's very easy to verify, so if you have time, I advise you to go and figure out the characteristic polynomial of A of t, which should be with constant coefficients. And that polynomial should produce that pair of conjugate eigenvalues. Okay. Now, the conclusion is that is lambda I are constant, and they satisfy the asymptotic stability condition, namely the real parts are strictly negative, okay, because they're at minus 1 over 4, and satisfy that real part of lambda I for all eigenvalues 1 and 2 are strictly negative. Note that for an LTI system, x that equals ax, this condition automatically implies exponential stability of the system, of the origin. However, for this system, even though A of t is bounded, even though the eigenvalues are fixed and they're on the open left half plane, we have unstable solutions. Therefore, the system is itself unstable. We have the following state transition matrix: e to the t over 2 cosine t minus e to the t over 2 sine t, e to the minus t sine t, e to the minus t cosine t. Okay. Again, it would be a nice exercise to verify that this is the state transition matrix corresponding to this A matrix. All we have to do to verify is that we have to show it satisfies phi dot equals A phi, okay? That is, it satisfies the differential equation described by the A matrix, plus it satisfies the initial condition phi 0, 0 equals the identity matrix. This is easy to see. Okay, plug in t equals 0, 1, 1, and these are zeros, and that satisfies. All you have to show, therefore, is that it satisfies the differential equation. That would prove that this is our state transition matrix. Now, let the initial condition be this vector 1, 0, and then the solution is x of t equals state transition matrix multiplying x of 0. x0 is 1, 0, therefore it picks the first column of the state transition matrix, which is here. Then x of t equals e to the t over 2 cosine t minus sine t. Okay, so that's our solution. And one look at the solution, due to that e to the t over 2 term, tells us that this x of t is growing unboundedly. In particular, the norm of x of t, since the norm of this vector is always 1 for all times, cosine squared t plus sine squared t, the norm of x of t is simply that e to the t over 2 equals e to the t over 2, and clearly, no matter how large you choose your constant to bound the norm, x of t at some point will always leave or go over that bound, so you can never bound the solution with a fixed norm. As a result, the system is unstable. Okay, so hence, even though the eigenvalues are fixed, the eigenvectors are changing in time such that they produce this unbounded behavior for certain initial conditions. Okay, so the lesson to get from this simple counterexample is that the eigenvalue locations of a time-varying matrix are not reliable. Okay, so they in general do not tell us anything regarding the stability properties of the system x that equals at of x. Okay, and now we'll talk about other checks of, or start talking about other checks of stability. By other, I mean checks that do not directly use the eigenvalue locations. Okay. So stability check without looking at the eigenvalues. Value computation. And we're once again back at the problem of studying stability for the LTI system. Okay, x that equals ax. A is a constant matrix. Now, before start discussing this subject, let's think a little bit about why do one need to check stability without looking at the eigenvalues, because we know that the eigenvalues provide a complete characterization of the stability properties of an LTI system x that equals ax. So by checking the eigenvalues, you can say for sure what the qualitative behavior of the system is. So since it's a very reliable, very good, and in most cases easy check for stability, it's worth thinking about why we would need other methods. Okay, well, first of all, from the theoretical point of view, it's interesting. Okay, so it has value in that. Second of all, it's always good to have many tools in your toolbox, even though one of those tools works most of the time. And thirdly, and that's perhaps the most important reason, that sometimes you cannot use the eigenvalue check, okay, for a system. The reason may be the following: you may have a very large system, okay, and very large system would mean a very large A matrix. And then when you have a very large A matrix, the eigenvalue computation could be expensive or sometimes not reliable, okay, from the computational point of view. Second reason would be that sometimes you may not know exactly your system parameters. Okay, you may only know, for instance, their ranges. In that case, you will not be knowing the exact A matrix, and then without exact A matrix you cannot compute the eigenvalues, okay? Or you may know the parameters of your system, but perhaps in time certain parameter values would change, okay, slightly. For instance, some inductance value would change due to temperature changes. Some resistance value somewhere in your circuit would change due to some outside influence. And then due to those changes, the eigenvalues that you computed initially may not be valid for later times. Hence, you would need, in such situations, another method, okay, that can be used for stability check. Now, let's try to motivate our method, okay, which eventually we will formalize under the name Lyapunov stability method. Now, consider an LTI system x that equals AX, okay, and x is in Rn, so we're talking about an nth order system. And now for this system, define the following function, Rn to R. So this function takes values, takes vectors from Rn and produces real numbers. And in particular, suppose that our function is x transpose x. Simply, this is the norm or the Euclidean norm square. Okay, so we can write therefore this as Euclidean norm square. First of all, since it's the square of the norm, it's never negative, okay? And it's zero only when its argument is zero, only for the zero vector. And for all other vectors, for all other non-zero vectors, this produces a positive number, okay? Note that v of x is always positive provided that x is different than 0. And at 0, v produces 0. Okay. Now, let's try to compute the rate of change of this scalar function, okay, with respect to time. In other words, what's v dot, and by v dot we mean, so what v does is it takes x vectors in Rn and produces a real number, a positive number, unless x equals 0. Now instead of putting here x, we put here x of t, and x of t is the solution of our system, starting from some initial condition. And then this becomes a function of time, v of x of t. And that function of time, what we're proposing now here is, let's differentiate that function of time with respect to time, okay? So what's the derivative of v with respect to time? So v dot equals d over dt x of t transpose times x of t, okay? And now x is a function of time. It's x of t, the solution of the system. And that can be written as x dot transpose times x plus x transpose times x dot, okay? So here all the x's are x of t. For simplicity, I just don't write t. Now this is scalar, v is a scalar, therefore its time derivative is also scalar. And you would notice that this x dot transpose x and x transpose x dot, they are the same thing. So instead of writing this, we could have written 2 times x dot transpose x. But for certain notational conveniences, let's keep it this way, okay? And then we can write this as, now what's x dot? X dot is a times x. Therefore, x dot transpose is ax transpose, which is x transpose times a transpose, okay? So this therefore produces x transpose a transpose x plus x transpose times x dot, and x dot is ax. We have ax, okay, which can be written as x transpose times something times x, and that something is A transpose plus A, our n by n matrix. Okay, this is an n by n matrix. We're multiplying with a row vector from left and a column vector from right, so that produces a scalar, as it should, because we're taking the derivative of a scalar function. Okay, now A is such that, suppose it produces a negative time derivative for V. Okay. Okay, now suppose at this point the matrix A is such that V dot, okay, once again, what's V dot? V is a function, okay, from Rn to R. And then what we do is we pass the solution x of t of the system through that function. And that generates a time varying, a function of time, scalar function of time, okay, V of x of t. And then we differentiate that with respect to time, and we obtain V dot, okay, again, a scalar function. Now, suppose A is such that that derivative V dot is less than 0, negative, okay? For all x different than 0. Okay, here is one instance. For instance, suppose that our system is 2 by 2 and the A matrix is our system is of second order, and the A matrix is -1, -2, 2, -3. Okay. Now for that A matrix, let's compute this sum, A transpose plus A. A transpose plus A equals -1, -2, 2, -3, plus -1, 2, -2, -3. Okay, this -2, that 2 will cancel, and the same will happen with the other off-diagonal terms. And we have -2, 0, 0, -6. Okay, it's a very nice structure. It's diagonal, even though A is not itself diagonal. So that allows us to write V dot, okay, equals x transpose, which is x1, x2, because we have two state variables, the system is of order 2, times A transpose A times x1, x2. A transpose A is that diagonal matrix, -2, 0, 0, -6, and that produces -2 x1 squared -6 x2 squared. Okay, so this means the following. This is our function V, okay, from Rn to R. From this function, we produce a function of time by passing through it the solution x of t. Okay, and then compute the time derivative of that V with respect to time, V of x of t, and we obtain V dot. And for this particular example, V dot is that number, -2x1 squared -6x2 squared. So that means, suppose that you have x of t, okay, x1, x2, and at some particular time here, this is your x of t. Okay, so what you do is, to figure out the decrease rate of V, okay, at that particular point, you get x1 of t and x2 of t. Okay, x1 of t is something, x2 of t is something, and then you plug those values here for x1 squared, and here we have -6x2 squared, and you compute a negative number, let's say -17. And -17 is the decay rate at that particular moment, instant in time, for your function V. Okay, and then x goes somewhere else. It will produce a new x1 and x2, and then again you plug in those x1 and x2, you compute something, -3, let's say, and that's at that particular instant the decay rate for your v. Okay. Okay, then, but no matter where you go, okay, no matter where x of t is, unless it's at the origin, at the equivalent point, it will always produce a negative v dot. Okay, so that means v is always decreasing. So this, which is obviously always less than 0, always negative for values of x except the origin. And now, what does that tell us from the stability properties of the system? X that equals ax. So the conclusion is easy to reach at this point. Now, what we have obtained is that v dot is always negative, okay? Except x equals 0. So that means v of x of t, okay? The solution of the system passed through that function, v, is always decreasing. Because its time derivative is always negative. So that means v of x of t is going towards 0. Okay, it cannot go somewhere negative because v by definition is the norm square. Okay, that's how we constructed it, x transpose x. Okay, so v cannot be negative. V cannot be negative. Okay. Therefore, it decreases, and where it's converging to is it's converging to 0. Okay, so this is 0, this is t, and this is our function v of x of t, and this is v of x of 0. As time goes on, this is where we start, v of x of 0, and since v dot is always negative, what we're doing is we're always decreasing, okay, toward the minimum value that v can take, which is 0. So this means that since v was norm square of x, therefore norm square of x of t, the solution, must be going to 0. Therefore, the norm of x of t must be going to 0. Therefore, by definition, the system x that equals ax is exponentially stable. Okay. Therefore, norm of x of t is going to 0. Therefore, x of t is going to the origin. And then, by definition, the system is asymptotically or exponentially, because they are equivalent for an LTI system, stable. Okay. Now let's emphasize certain key observations regarding this simple example. To figure out that the second order system x that equals minus 1 minus 2 minus 3 is asymptotically stable. Okay, we didn't exactly compute x of t by first computing, let's say, state transition matrix and multiplying that by the initial condition. We didn't compute x of t explicitly, nor we computed the eigenvalues of the A matrix. Okay, instead we just analyzed the behavior of a scalar function that can never be negative. Okay, and whenever this scalar function goes to 0, it would mean that the solution itself goes to zero because our scalar function was simply the norm square of the state x of t. Okay, stable. We have neither computed the solution x of t, okay, explicitly, nor the eigenvalues of the A matrix lambda I. Okay. In fact, we didn't even compute v of x of t. All we computed was its derivative, lambda I. Instead, we showed that a positive definite function of the state v of x always decreases along the solutions of the system x that equals ax. Now this last sentence means decreases along the solutions of the system. It means that instead of x you plug in x of t, and x of t is not an arbitrary function, it's the solution coming from our LTI system x that equals a of x. So when you plug in x of t inside that function, you obtain a function of time. And that function of time, that scalar function, we have shown that always decreases, okay, by looking at its derivative. Okay, so this idea is very powerful. And it's especially important for nonlinear systems and also for linear time varying systems, because we know that for the nonlinear systems we don't have the eigenvalue check. Okay, so this idea is very powerful, and it's discovered by Alexander Lyapunov. Okay. Who lived between 1857 and the end of First World War. Okay, now we will eventually generalize this very powerful idea that we try to visualize on our very simple second order system. Okay, we will try to generalize that to more higher order systems, okay, for more general situations. But before that, we have to do some review of the positive definite matrices. And why is that? It has to do with the following observation. What was essential about our function, okay, v of x, in the above analysis? So let's try to extract the key properties of v of x that allowed us to make the conclusions that we have made. First of all, it was positive, okay? Positive definite. In other words, it's positive for all non-zero x, and at x equals 0, it's 0. So that means that's a positive definite function, and whenever it's decreasing towards 0, it means that it has to take the solution with it toward the origin. Okay. Hence, the generalization. Okay. V of x equals x transpose px, where p equals p transpose is a positive definite matrix and also symmetric. Positive definite. Okay. So once again, we worked with, here's our v, we worked with what? V of x equals x transpose x in our example. Okay. So written in this form, it produces, or it can be written as x transpose times identity times x. And this is the square of the Euclidean norm. Okay. And we show that square of the Euclidean norm decreases along the solutions of the system. Therefore, the norm should decrease. Therefore, x of t should go to 0. Now, the one way to the first guess would be that if your system is asymptotically stable, then the norm square would always decrease. Therefore, the norm, Euclidean norm, would always decrease. It turns out that it's very easy to find counterexamples. It increased for our case because it was a specially constructed numerical example. But in general, Euclidean norm would not necessarily monotonically decrease along the solutions of a asymptotically stable system. Okay, but it turns out that a generalized norm, okay, in this case x transpose px, then you have to take the square root. A generalized norm in this sense, where p is a positive definite matrix, would always, or you can always find some p and construct some generalized norm which would decrease along the solutions of the system, and that result will be eventually formalized into Lyapunov stability theorem. Okay, and that theorem we soon enough start talking about. But before that, since it heavily depends on positive definite matrices, let's quickly review some key properties of such matrices. Positive definite matrices. Okay. Now a symmetric n by n real matrix, let's call it Q, is said to be positive definite. Okay, if the function x transpose qx is positive definite with respect to x, where x is a vector in Rn. Okay, in other words, if this object, okay, x transpose qx, which is a scalar, is always positive, okay, unless x is 0. Okay, so for all x in Rn and x is non-zero. It's called positive semi-definite if x transpose qx is never negative, okay, for all x. Okay. And negative definite and negative semi-definite are defined analogously. Negative definite if minus q is positive definite, and negative semi-definite if minus q is positive semi-definite. Okay, so that's the definition for positive and negative definite and semi-definite matrices. Now, given a Q, given a symmetric matrix, how can we check its positive definiteness or positive semi-definiteness? Here are a few simple tests. The following statements are equivalent. Okay, for a symmetric real matrix for Q transpose equals Q in real n by n. Okay, one, Q is positive definite, and the shorthand notation to indicate that a matrix is positive definite is simply writing Q is greater than 0, and sometimes you may see things like that. P greater than Q, P and Q both symmetric real matrices, and this simply means that P minus Q is a positive definite matrix. Okay, so that's one. This is equivalent to, in terms of the eigenvalues, that all the eigenvalues of Q is positive. Okay, first of all, since we're dealing with a symmetric real matrix, all the eigenvalues are real. We cannot have any complex eigenvalues. And if all those real eigenvalues are positive, then and only then Q is a positive definite matrix. All eigenvalues of Q are positive. Okay. 3. The determinants of all upper left submatrices, sometimes called leading principal minors of Q, are positive. Okay, what we mean by that is the following. Suppose Q is the following 3 by 3 matrix: A, B, C, D, E, F. Okay, so this is the smallest matrix So its determinant must be positive. Its determinant is itself, so we require that A is positive. And then we go to the second left submatrix, which is that 2 by 2 matrix, whose determinant is AD minus B squared. So that also needs to be positive. And finally, the matrix itself, namely Q, it should have a positive determinant of Q. If all these scalars are positive, then Q is a positive definite matrix. Okay, and for there exists an n by n non-singular real matrix H such that Q can be written as H transpose times H, such that Q equals H transpose H. Okay, so being able to write Q in that form could be quite beneficial for certain points in our analysis later on. Okay. And finally, for a positive definite matrix, there's a relation between the Euclidean norm of X and the value X transpose QX. So for a symmetric positive definite Q, we can write the following. Again, this will prove useful in our later analysis. Lambda min Q, so this is the smallest eigenvalue of Q, times the Euclidean norm X transpose X, Euclidean norm square, which is X transpose X. So this lower bounds X transpose QX, and likewise X transpose QX can be upper bounded by the largest eigenvalue of Q multiplying X transpose X, or the Euclidean norm of X's square. Okay. Now, after this review, we're now ready for the Lyapunov stability theory for linear systems. Okay, and that we start talking about in our next lecture.